Okay, I think now it's being recorded. Right. Uh, is it fine?
Yeah, it's recording now.
Yeah. Right. Number one is the convergent plate boundary, where two plates are moving towards each other. So that is what you call the convergence. So two plates are moving. In this case, this plate is also an oceanic plate, and this plate is also oceanic plate. Okay, two plates are moving together. That is convergence. And the second situation is transform plate boundary. That means it's a single plate, but it's kind of fragmented or ruptured, like, right. Once you have this rupturing, that is what we call the faulting, right? Fault, F-A-U-L-T, fault, right? It's a geological term. We call faulting. It's a it's a physical phenomena where brittle deformation is happening. We call it a brittle deformation. That means the plate or a rock layers are breaking. So, being these plates are composed of rocks, there is fracturing here somehow, right? Due to various reasons like compression, extension, like many other things. When the physical properties of these materials are changing with respect to the temperature, pressure, and other tectonic conditions prevailing in the earth, these plates can be fractured. So once these plates are fractured, uh, based on that other forces prevailing in the surrounding, these plates can be moved in parallel directions. So that is what you call the faulting. So here, a single plate fractured, which is moving in one direction, like this way, towards left hand side, and the other portion is moving to the right hand side. So that is what you call faulting. So this type of faulting situations are called transform plate boundaries, or in other words, transform faults. So that is another plate boundary that we have in the planet. So that is the second situation. And the third situation is the divergence. Divergence or divergent plate boundary. That means the two plates are moving away from each other, right? They are moving away. So this plate is moving towards the left hand side, and this plate is moving towards the right hand side. So that means they are under divergence, moving away from each other. And what is happening in such situations is some special. It's a kind of a special situation where what you have, magma intrusion is happening, because uh, you are diverging two plates means you are creating an additional space somewhere here. Okay, some additional space here. So that means it's a kind of a low pressure region. So always this magma is high temperature and compressed due to pressure with the depth, right? So from this depth, magma is coming up. This magma is coming up, and that magma can penetrate through the open space and dump into the ocean floor, right? So this magma is being dumped onto the ocean floor here, right? So that is happening every time. Even now, it's being happen, and this magma accumulates as under ocean volcano or undersea volcanoes, and make some kind of volcanic mountains. Magmatic materials are dumped so that they create some mountains. So these mountain-like feature prevailing in the depth in the oceans is called mid-oceans. So these are mid-ocean ridges. Sorry, mid-ocean ridges. Okay, those are mountain ridges, but existing in the on the ocean floor. Therefore, we call mid-ocean ridges. So in the middle of an ocean, we have mountains. So these are the mid-ocean ridge mountains. Uh, Mostly they are associated with the middle of the ocean. So all the oceans we have, 7 oceans. Every ocean contains this type of mid-ocean ridges. So this is the third plate boundary, and the fourth situation. Again, it's a convergent plate boundary, right? It's convergent, but the difference than the first case is one plate is oceanic, this one is oceanic, and the other one is continental, right? Continental plate and oceanic plate are being converged together, uh, and that is also a convergence, right? So what is happening there? As I mentioned, the oceanic plate is always heavier, so therefore it tends to move downwards, right? It moves downward towards the mantle interior, and at a certain place with the depth and the pressure and the temperature conditions, the oceanic plate cannot bear anymore. Its physical conditions become weaker and weaker as the subduction continues, right? This subduction continues, the physical properties gets weakened, and therefore at a certain depth this plate breaks, right? This is a place where the breaking of the plate happen. So the broken part, the remaining broken part further subducts into the deep mantle, whereas the other portion, the remaining portion which is attached to the surface is resting there, but it can't rest at once. What is happening is just to maintain the balance, because it is a sudden break. So just to maintain balance, what happens is it goes backward. So it tends to move backward just to maintain the balance. We call isostasy. To maintain the isostasy, it goes back. That means the subducted portion, one portion of the plate, that is the broken slab, comes up towards the surface. So this is what we call upliftments, right? So this plate is being uplifted. That means coming backwards, uh, trying to come backwards, but it can't come backwards completely, but slightly it can come back. And what happens is it will create sort of a ridge-like feature at the trench, at the margin, right? So because of return of this slab, so that is happening. And at the same time, what is happening is during the subduction, so this part gets heated, and also by frictional forces, it tends to melt the uh, existing materials around here. So this part is not only the oceanic or the continental part, this region, it always contains some sediments as well, because this is the margin. So this margin always contains lot of sediments, right? Sediments means the erosion remnants coming from the surface, right? Coming from the continents, right? So all these materials which are existing there is going towards the ocean basin, and these sedimentary materials are accumulated here, and all these accumulated materials, like the ones which are available in this region, are dragged during this subduction, right? These sediments are also being dragged downward during the subduction, and therefore this area is sort of a mixed materials region. So you have sediments, you have oceanic crust, you have continental crust, everything is there. So all materials contains different mineralogical features. For example, iron magnesium rich portion, iron calcium rich portion, as well as aluminum rich portions, right? Everything is there. So they tend to get melted due to high temperature prevailing there at different times. Why it happens at different times? Because these materials melting points are different, because those are having different compositions. uh, Silica rich materials, iron rich materials, aluminum rich materials, right? All of these materials temperatures are different, melting temperatures are different. So therefore uh, several batches of magma can be formed as a result of these various stages of melting. So, as I mentioned before, some special geological conditions are required uh, for for generation of different minerals, right? Is satisfied in this type of regions, because various temperature conditions, various materials, they are subjected to melt and mixing and everything. So this happened at various time intervals with respect to this subduction, right? So anyway, some volcanoes are produced there, and these volcanic materials are also being dumped at the margin, and they also create some new volcanic mountains, and these are always arranged or located along the parallel to in parallel direction to the this margin, this continental margin. So this continental margin, volcanoes are generated. For the best example is the Andes Mountains, right? The Andean region is a typical uh, place where you can explain this type of convergence situation, right? The oceanic and continental convergence. So that is a very active region, and very obvious in the Earth's crust. So we can find a lot of evidence for this type of uh, continental activities, convergence activities. Okay, that is the fourth one, and the fifth one, which shows here, is the rift zone, continental rift zone. Continental rift zone. What is rift? The rift itself means some fracture, right? Fracture means breaking. So the continental plate is broken there, right? You can see the plate is being broken, and this happens due to extensional forces, right? For example, when the same plate is being extended in two opposite directions, right? If you drag this one plate in two edges, at a certain point, it tries to break when its plasticity limits exceed. So therefore, fracturing happens, and that fracturing also causes some low pressure region to generate, for example, in a place like here. And then what is happening is, again, the squeezing magma will penetrate through that fracture, and some uh, some some magmatic flooding can take place around there, right? So therefore, there are some regions where we call flood basalts are there, right? Basalt means a magmatic material crystallized and form a rock, igneous type of a rock, basalt. Here also you have the in the mid-ocean ridge, also you have basalts, mid-ocean ridge basalts we call MOB. And that basalt is different from this basalt because the composition is different little bit, because this is continental region and this part is oceanic region, so compositions are different. So they are, anyway, these basalts are called flood basalts, continental flood basalts, uh, and this is also caused by extensional forces, right? So that is the fifth one, and the sixth one is actually, uh, what is the sixth one, the remaining one?
Convergence between two continental
Yes,
uh, plates.
plates. Yeah, that's right. That is the one missing there, where two continental plates are converging. Actually, indirectly, this is shown here because sometimes when this subduction continues, if these continental plates can, sorry, these oceanic plates, all oceanic plates can be subducted, right? All of these oceanic plates can be subducted with time, little by little. Then what happens, all these sections, all these areas will be coming closer and closer, right? They are coming closer and closer towards the this continental uh, plate, right? You have this continental plate because continental plate doesn't have, I mean, nothing happens to this continental plate. It's being grown only, right? It extends little bit, it extends toward this direction. Why does it extend? Because as the subduction goes on like this, if the subduction continues, what is happening is, so many new materials are generated here, volcanoes and other new materials, melted materials, parts, everything accumulates here while subduction is going on, right? So this is a two-way process, destruction of materials as well as generation of materials. So there should be some balance, as I mentioned, there is no way for the mass destruction. Therefore some balancing is there. So when this, if there is time for this to continue over a long period of time, some hundreds of millions of years it will take. So what could happen? This is an oceanic plate, and you know this oceanic plate is also connected to a continental plate somewhere in this direction, right? Like this continental plate, there should be another continental plate this side, because you know oceans are in between the continents. So always oceanic plate is connected to a continental plate in one side. So as the subduction continues, this continental plate which is available in this region, okay, come closer and closer, and it will be coming closer and closer, and will collide, will hit with this particular continental crust, because this continental crust is also little bit moving towards this direction while growing of new materials, right? New materials are being connected to that. So there will be motion from this direction, like this way, and another uh, one like this way. So what is happening? They will collide. So once the two continents are being collided, what can happen? Both are of same density, almost same density. There is no way for subduction because these are continents. So what can happen is it just collide. Two continents will collide like that, and with this collision progress, right? This when this collision progress in the two directions, gradually this will build up some mountain like feature here, because there is no other space to accommodate. So only space to accommodate is bending like this, right? So bending like this, so that means you are automatically forming a mountain in this region. Okay, so this is how the Mount Everest or the Himalayas are generated. So Indian plate hits with the Eurasian plate, both are continental plates, and there is no space to accommodate. So only thing is they are just bending upward like this, both plates. So both plates contribute to uplift this type of mountain range, and this mountain range is generated there. So alpine mountains, Himalayan mountains are all similar to this sort of collision. Even ours, Sri Lankan tectonic situation is also same. Ours also related with continental collision. So we also have a lot of mountains. For example, in the central hills, this type of activities have taken place to build the mountains. So colliding means again like rubbing two materials together, like, so then again the friction comes into effect, and huge frictional forces are there, and
Excuse me, sir.
yeah.
Yeah, Sri Lanka is not on the boundaries of the plates, right? How
Yeah,
can the mountains
yeah,
can be
again
formed?
same answer is there. It's not the current situation, right? Sri Lanka was
Uh,
at a boundary about 550 million years ago. That is the time where the collision took place, not now. Okay, it's 550 million years ago Sri Lanka was at a boundary. I mean it's the Gondwana, the supercontinent Gondwana. So I think uh,
yeah,
very beginning
yes,
we
yes.
just explained some facts about that, right? So now we are connected. So being collided two plates, right? For example, here one plate and this plate. So at that time Sri Lanka was somewhere in this region, part of the Gondwana. It's part of the East Gondwana, right? So this East Gondwana and West Gondwana, this one collided together, right? So this collided together and formed mountain ranges. That is what you call the Mozambique Belt. And of that part of Sri Lanka was there. Later on, this was fractured again by hitting of a plume, as I mentioned at that time. Then what happens? The Sri Lanka containing part moved. Actually, it moved this direction, right? Now we are away from a boundary. Now we are away from a boundary and part of a new plate like this. But at that time,
So does that mean that mountains in Sri Lanka? So does that mean that mountains in Sri Lanka are older than Himalaya?
Yes, of course, very old, older than Himalaya.
Yeah.
Himalaya is
Okay.
very young.
Okay.
Yeah,
Right.
yeah. It's about 100, 200, even less than 200 million years. Yeah, definitely. Ours are 550 million years old at least. But the material composing the mountains in our country, the rocks, are much older than 550. That means even up to 2000 million years, rocks are there, ours. So that means the materials were already existing, and these materials were collided at 550 million years time, and at that time these mountains were formed together. Right? Okay.
Hello, sir.
Yeah. Any question?
Hello. Yeah. Uh, if we consider about the mountains in Sri Lanka,
Yeah.
uh, is there any possibility to find some diamonds around the central hills?
Actually, there is no evidence found. There are a lot of research has been carried out, but we did not have diamond because the pressure conditions are not sufficient to form diamond. Only the temperatures are high. Collision means always frictional force. The dominant force is the friction. So a lot of heat is generated rather than pressurizing. So therefore, ours contains a lot of rubies, sapphires,
Ah,
like high temperature gem varieties, but not the high pressure gem varieties like diamond. That's the reason. If we
okay.
were subjected, I mean, we were under subduction like tectonics, then we could have had some diamonds definitely, because we have a lot of graphite. Graphite means the sedimentary materials. When they are brought into the deep interior, they are get converted into diamond. Their structural change happens without chemical compositional change. Carbon is carbon, right? But the structure changes, therefore it becomes diamond. But in our case, the pressure conditions are not enough, because it's like 10 kilobars, the maximum pressure our rocks exposed, our rocks experienced. It's 10 kilobar means a depth of like 30-35 kilometer depth. But the temperatures are has reached even up to 1000 degrees Celsius. So that is more than enough to form corundum or ruby or sapphire like family, aluminum oxides as the gem variety, but not the form of diamond of carbon. So therefore, we don't have diamond to find in gem scale, in gem quality, but very tiny diamonds could be found as inclusions in some other minerals. But still, that is very rare. But I have never seen any in any research on occurrence of diamond in our rocks. But in some other countries, even in collisional settings, very tiny, very rare diamond could be found, because that is not related with actually the graphite diamond conversion. It's just because of the mantle magma, which contains already diamond. Because mantle in the deep levels, diamond is existing as I mean the carbon is existing as diamond at the very deep interior in the mantle. So this magma can come up carrying some of those tiny diamonds, right? Such diamonds will be trapped in rocks in minerals where you can find them in very micro scale diamonds. So those are micro diamonds actually, not the varieties that we expect. But the magma which is coming from very deep interior, like in Africa, we call them kimberlite magma, kimberlitic magma, which contains a huge amount of big diamonds, right? So that's why in African countries you have these places where these diamond mines are there, right? So the diamond mines means they are mining a conduit of kimberlite magma. That means a magma chamber being mined, where you have a lot of diamonds collected there. Even on the surface, you have diamond like what you see on gravel, like when we cut a slope, right? because that much of diamond is available in the mantle even now, but it's very, very deep, more than maybe more than 200 kilometers deep in the mantle. These diamonds, very difficult to bring them up, but only possibility is naturally taking them up by the kimberlitic flows of magma, where these diamonds are also being brought to the surface. Other than that, what we get is only the inclusion phases of diamond, or otherwise the graphite diamond conversions. For example, the Central Asian orogenic belt, somewhere uh, in the Russia, in the Central Asia, like where you can connect uh, Russia and this Kyrgyzstan, Kazakhstan boundaries. There is some subduction, earlier old subduction places are there, where now people excavate diamond in large quantities, because that region was subducting some million years ago. I mean, some hundreds of million years ago. But now that place, that region is now exposed to the surface. For example, I mentioned in this diagram where once the subducting plate broken at a region like here, it will uplift, I said, right? It will uplift and it will come to the close to the surface, right? Directly it can't come to the surface, but later on what is happening is erosion will take place from here, right? Like the mountains are being eroded, all these places, once they are exposed to the surface, can be eroded. So once this erosion continues for 100 million years time, like this deeper part, relatively deeper parts like here, can be exposed to the surface. So this deep part always contains some high pressure minerals like diamonds, I mean graphite diamond transitions. So they can be automatically exposed while this when this the overlying crust being eroded away, right? So that's how these deep materials are being brought to the surface. So this is a natural process, uh, other than the volcanism, right? Volcanism can bring the deep material from the mantle like here onto the surface, directly onto the surface, like in Africa. But in the places like Kyrgyzstan or Kazakhstan or the Eurasia or the Russian region, uh, that those diamonds which are available there are brought by this type of subduction and upliftment processes, right? So there are, that's why we call in general, for generation of gems or occurrence of gems, we need some special geological conditions. So these are the special, these sort of things are the special geological conditions that we should have for these gem varieties to be exposed. Most of the gem varieties are very much related with temperature situations rather than high pressure situations, except for jadeite, like jade. I think you know jade, because that is also a high pressure variety, pyroxene variety. So these are related with subduction, like that is high pressure. But other many other gemstones, you have spinels, zircons, and ruby, corundum. All these popular gem varieties are very much temperature sensitive materials, because they are formed at higher temperature conditions. Even we have sapphire in Sri Lanka. Uh, don't get confused with sapphire. Sapphire is a I think the composition is magnesium aluminum silicate, which is found in ultra high temperature metamorphic rocks. Ultra high temperature metamorphic rocks. Ultra high temperature means the rocks which were subjected to very, very high temperature conditions, greater than 900 degrees Celsius. Usually, when the rocks are subjected to temperatures more than 900 degrees, what happens is the rocks get melted. So get melted means it forms magma, right? So no longer it will exist as a solid rock. It will become a magma. But some rocks are there, depending on their bulk chemical composition, they don't get melted. That means they survive melting even under high very high temperatures in excess of 900 degrees. Such rocks are called ultra high temperature rocks, and those rocks can generate some special varieties of minerals. For example, sapphirine is a very nice blue color mineral. I think it's found even in gem gravel in Ratnapura even, because that those minerals were found in our rocks. I mean, occurred in our rocks some hundreds of million years ago in our rocks. During that Gondwana time, these minerals were formed. But now, after erosion and being they are resistant to weathering or erosion, you can find them with the gem gravel in Ratnapura, right? Gem beds in Ratnapura. So these are ultra high temperature minerals, and there are some other ultra high temperature minerals as well, but very rare. Uh, so anyway, we have such varieties as well, but not the varieties like diamond, because they are more sensitive to high pressure conditions. Okay, so these are the types of plate boundaries existing in the Earth, where we have different different geological materials interacting, as well as geological conditions we can expect, and also the pressure temperature, the physical conditions, the pressure temperature conditions are the most important features, most important factors related with mineral formation. So therefore, in these all these different tectonic activities, you can see various types of minerals formed, right? So as I mentioned, there are about 3,000 minerals all over the world, all over the planet, and these 3,000 minerals can be found in different tectonic places, right? Some are common for all tectonic places, but some are common only for few or one tectonic boundaries, and out of which we have defined like 152 to 200 maximum varieties as gems. Why we categorize them as gems is, you know already, because they are rare, durable, and beautiful, right? Those are the three features for a mineral to be called a gemstone, right? Rarity should be there. That means they should not be available everywhere. If it is available everywhere like quartz or feldspars, we don't value it, right? It will not be a precious stone, and it should be durable as well. So if a mineral like feldspar, it will decay into soil very quickly, right? So that does not uh, qualify for a gemstone, right? So the mineral should be durable, as well as it should be beautiful also. Once cut, it should have a nice appearance. So those are the main requirements for a mineral to be called a gem variety. So these are not common for all the minerals. Therefore, we can't term all these minerals as gems. So it's just about 150 to 200 varieties, precious and semi-precious, as you know, depending on their quality and depending on their occurrence, and again rarity, and the beauty and other features. Uh, we can term them again into two groups: precious stones and semi-precious stones, right? All these are anyway in general are minerals, right? So anyway, different compositions are there. When you learn about the mineral varieties or the mineral groups, you will learn all these chemistries and all features there, because for example, spinel is a silicate. Sorry, spinel is a oxide. Yeah, spinel and corundum is oxide, but the other like pyroxene, jadeite, or peridot, all the other ones are silicates, right? So this categorization again depends on the mineral composition, right? Whether it is a silicate or oxide or hydroxide or sulfide, likewise, right? So we will I think you will learn about these things later on. uh, and these different minerals are characteristic for different tectonic boundaries, right? So out of these tectonic boundaries, we will go to the first one one important boundary, that is convergent boundary, right? So convergent boundary can be three types, like as we mentioned, ocean collision, right? Ocean collision, that means oceanic plate collision, that is possible. And the second possibility is continental plate and oceanic plate collision, that means both crusts are continental and oceanic, right? In opposite types, right? The other one is continent, both are same type, continent type, oceanic type, oceanic type, or continental type, right? So these are the three types of convergent plate boundaries. We just looked at the figure as well. And so we'll see the ocean collision first. Ocean collision, some features of ocean collision, where you can see one oceanic crust is colliding with another uh, oceanic crust, right? Two oceanic crust is there, but you know already, being both are oceanic crusts, the the densities are almost same. So then we have the both plates has to decide which one to subduct, because underlying is the mantle, unlike the continental thing, because continental plates have a root to the mantle, like here, right? They have a root to the mantle, therefore they are very stable. But oceanic crust does not have a solid root to the mantle, because it's very thin here, right? It's very thin, this part. So therefore one plate definitely subducts beneath the other one. So the more weaker one, rheologically weaker one, that means the weak plate, in physical conditions, the weak one will bend. The first it will bend and then subducts beneath the other oceanic plate, right? There is no much control on the density, because both plates are almost same density, but the more weaker one tends to bend and subduct beneath the other one. So there two oceanic plates collide, and one runs over the other, which causes it to sink to the mantle, forming a subduction zone. So subduction zone is formed. So this is the subduction zone. This part is the subduction zone. This Since it is a subduction, right? Intermittent trench. Okay, because of the subduction zone. Right. So this subducting plate is bent downward to form a very deep depression. So the depression is formed. That is what the trench is called. Depression. For example, the Mariana Trench. The Mariana Trench, the deepest trench we have in the Pacific Ocean, is a result of this type of tectonic activity. Okay. So in this trench, you have a lot of materials accumulated, because during this subduction you are dragging the sediments as well, because there are so many sediments. For example, shells, calcium carbonate materials, silicate materials, everything is there. Oceanic animals, crusts of animals like shells, everything is being broken down, being brought down with this subduction. For example, you know the limestones, right? Limestones are found in oceans, right? Because of calcium deposition, calcium carbonate deposition, as well as a result of uh, the depth of oceanic creatures like shells, and their shells contain calcium carbonate, and these calcium carbonates are deposited or precipitated in the ocean floor, and this oceanic material forms a special sedimentary type of a rock called limestone, right? So these limestones are being subducted together with this oceanic part, and they are subjected to higher temperature conditions here, right? So then what happens? They change their form. That means their minerals converts into new minerals, right? So these limestones, although it's calcium carbonate, that means calcite or aragonite. There are two minerals called calcite and aragonite carbonates. So when they goes down, they get changed. The entire rock becomes a different type of a rock due to this high temperature and exceeding pressure conditions. So this limestone converts into a rock called marble, right? You know marble already. You know marble because the Taj Mahal was made with marble, right? Marble is in Sinhala we call Kirigarunda, right? It's a metamorphic form of limestone, right? It's more robust rock than limestone. So this conversion takes place. For example, sandstones which are available in the ocean floor, sandstone, valley gull, okay? These sandstones, because of accumulation of sand particles, the sedimentary rock is formed. That is sandstone, and that sandstone is brought down into the subduction zone, and due to high temperature and pressure conditions, it also converts into another type of a rock. That is what you call quartzite, right? What is quartzite? Tiruvana, right? Palingu. It's a gem also, right? So that material is converted by sandstone because of high temperature conditions and pressure conditions prevailing in the subduction zone. This type of conversions are happening. Not only that, there are so many other types of conversions are there. What else? Clay stone. Clay stones are also present, and these are also turned into different type of rocks. For example, there is a rock type called condylite. You will learn about these things under petrological aspects in practicals as well. Once you are allowed to access the labs, you will see all these rock types in physical forms in the laboratory. And condylite, or the type of a sillimanite bearing gneiss, right? So garnet, sillimanite, gneiss. So these rocks are a product of this type of deep subduction. No, sorry, not deep subduction, shallow subduction, but just conversion due to high temperature conditions prevailing in these regions. If it goes to very deep interior, very different rock types will be formed. For example, peridotites, sorry, not peridotites, eclogites, the rock variety called eclogites, which contains huge amount of garnet, pyroxene, and amphiboles. And these are high pressure varieties of garnet and high pressure varieties of amphibole and pyroxenes. For example, spacetine garnet, calcium rich garnet, and also pyroxene variety, high pressure pyroxene variety, sodic pyroxene, sodium rich pyroxene, which we call jadeite, or in gemmology many people call jade as jade, right? So these are another type of high pressure type of variety. So all high pressure, high temperature varieties can be formed due to the subduction at various depths. If it is shallow depth, then some different forms like we mentioned before. And if it comes to the deeper levels, much deeper levels, even diamond can be formed. In some eclogites, there are some inclusions of diamond. That's what I mentioned about the Kyrgyzstan, Kazakhstan, Russia, southern part of Russia, like regions. They have diamonds, but they are not very big diamonds like what you have in Africa, but micro diamond to some few, maybe some 1 or 2 centimeter big diamonds are also found, uh, depending on the pressure conditions they have been subjected to, right? So very deep levels, when it goes, all these conversions can take place. So the world's deepest parts of the ocean are found in along trenches, because these are the places where you have the trench formed, where you see the Mariana Trench, for example. It's about 11 kilometer depth, 11 kilometer deep, and the Japanese islands also subducting segments are there, and Solomon Islands, these are also formed as a result of subduction. You see, once the subduction is taking place, I mentioned that some magma eruption is happening. this magma will be on the trench region, near the trench region, and then after they are cooling, the these magmatic islands are formed. These are called island arcs. We call them arcs because they are products of volcanism, right? So you have some tiny uh, island for chain formation. Chains of islands are formed. So these are typical feature of subduction plate, where close to the margin you have these chains of islands. So Japanese islands are a product of that. Solomon Islands are also a similar sort of a product. So it's related with subduction. So ocean plate collision uh, causes this type of tectonic and lithological or rock variations and minerals formation as a result of a subducting plate. Okay, so this is the ocean plate collision, right? Do you understand that part, the ocean plate collision? Right. So we will move to the other part, that is continent ocean collision. So one part is the continental segment, and the other part is oceanic uh, plate, right? Oceanic crust and continental collision. Here you have the oceanic crust, and you have the continental crust here, and these two are being converged, right? They are coming towards each other. Convergence is there. So oceanic crust being high dense, what is happening is it naturally it will tend to subduct. It will tend to subduct because of high density. So it is moving down. The similar features that we talked about will be happening. Magma generation because of this subduction. So always this subduction causes dehydration. Right? Any type of subduction causes dehydration. Dehydration of minerals, actually. Dehydration of minerals, because the subducting slabs contains rocks which are composed of different minerals, various minerals, and these minerals there are two types of minerals generally: hydrous minerals and anhydrous minerals. Anhydrous minerals means minerals which do not have water in it, in the structure, right? Hydrous minerals means they have some water molecules or water components in their structure. This water doesn't need to be, to be called it a hydrous mineral, it doesn't necessarily to be H2O, right? There can be OH groups attached to their structure. That is also enough, because once you have these OH minerals, later on with high temperature conditions, they tend to dehydrate. That means that OH part from the structure will be released, removed, and it will bond with another hydrogen atom and form H2O. That means water can be generated from minerals. You may have heard that in old times, some of our giants made rocks into water, right? Converted rocks into water, or they squeezed rocks and got water out of it, right? අහලා තියෙනවද ගල් වලින් වතුර ගත්තා කියලා ඉස්සර යෝධයෝ, right? මේ වගේ දේවල් වලට වෙන්න ඇති මං හිතන්නේ. මන් දන්නේ මේක කරන්න පුළුවන්ද කියලා. හැබැයි when you have a lot of hydrous minerals in the rock, you can heat it up and get water out of it, right? Because dehydration reactions can take place, right? So water is generated. For example, amphibole, biotite, mica, all these have OH groups. They have OH groups. That's why we call them hydrous minerals, right? So this dehydration can happen. Also, not only that, decarbonation can also happen. Decarbonation also can happen. For example, calcium carbonate is a carbonate mineral, calcite. Once it is being subducted and subjected to, not necessarily to be subducted, but whatever, if it is the material is being is subjected to high temperature conditions or heated, that carbonate part also changes. That means it evolves. It make for the carbon dioxide to be evolved, right, out of carbonate part. So this is also possible. So dehydration as well as decarbonation can take place during these high temperature conditions if the rocks are subjected to. So here the same thing can happen because this oceanic materials contains a lot of hydrous minerals as well as carbonate minerals. So decarbonation and dehydration both can take place, and these dehydrated minerals will become anhydrous minerals, and they release water, and this water is circulating within this region, and also being they are hot, this water they can absorb other materials from the surrounding as well, and they can come up as a solution, right? Because they are I mean other materials are dissolved in that high temperature water. So therefore we call them hydrothermal solutions. Hydro means water, thermal means temperature. So high temperature water means hydrothermal solutions, because they can easily dissolve materials. For example, they can dissolve heavy ions, even gold like sulfides materials, and gold like materials can be dissolved there. So that's why you have the 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 deposits, mineral deposits like sulfide deposits, carbonate deposits. No, sorry, not carbonate, sulfide deposits, mainly sulfide deposits actually. For example, galena, lead sulfide, azurite, and what is it? Zinc sulfides, like zinc sulfide, like deposits, gold related deposits, and cobalt, copper related deposits. All these are related with these hydrothermal solutions. These hydrothermal solutions can be generated due to this type of activities, the hydrothermal solutions, and plus magma is generated. And this magma is dumping the materials onto the continental crust margins and form huge mountains. Okay, so we call them partial melting as well, because this melting is not complete. If it is complete melting, everything should be melted in this region. Okay, everything should be melted in this region, but usually it happens partially, right? Not the whole entire part get melted, only place to place get melted. So these melted portions will accumulate together, and being they are having low density compared to their surrounding rocks, they tend to come up as magma flow. We call them buoyancy. That means the flowing or the floating nature, right? It's like floating, right? They are coming up within the squeezed lithosphere as magma flows. So this partial melting, and also it brings
Excuse me, sir.
overlying mantle. Yes.
Can you just explain a little bit about this partial melting? Like I saw one of theory. It's
Yeah.
called pretend rock, and it was shown with the four pictures that like the basically it says the original components of the white candle wax and the black plastic and the green bleach glass and the aluminum wire. And the second, after the heating the 50% of 50% centigrade for the 30 minutes, only the wax has been melted. And the third, what the number C, after heating 120 degrees for the 60 minutes, much of the plastic has melted and two liquids have been mixed. The number
Mhm.
4, it says the liquid has been separated from the solid and allowed to cool to make a pre-trained rock with the different overall composition.
Yeah,
It's,
actually, yeah, it's just an example you presented for the partial
yeah,
melting. Uh, it's the partial melting means actually melting at different points, different temperatures. That's the idea behind that. Once you have a mixture, different types of varieties, materials, their melting points are different, as I mentioned, right? That means once you are continuing heating, everything does not get melted at one point. So one material may start melting at a low temperature than the next material. So once you reach the low temperature melting point, that particular material which is sensitive to that melting get melts, the other one remains solid. So that means you are making a partial melt out of the entire material. So once you form the melt, still you have a solid component left behind there. So that's the idea behind the partial melting. So the rocks are also same. Once you have a rock, it contains various minerals, as I mentioned. So you have different types of minerals there, and these different minerals have different melting points, right? So these different melting points are reached at different time intervals once you heat this material. So when you heat this one, uh, for example, if this has the melting point around 500 degrees, so it will first start to form a melt, right? So one melt is generated there. So at that time, all the other minerals are, all the other components are remaining hard, remaining solid, right? So when the temperature further increase like 600, then another mineral starts to melt. So okay, so this is another melt. So one melt is formed, another melt is formed. So you keep continuing the heating. That means the subduction is also continuing, right? So that means you are going more deeper and deeper levels. That is equivalent to you are increasing the temperature, because when you go deeper and deeper, the temperatures are increasing little by little. So it's like you are continuously heating the material. And then at another instance, the other melt, the other material will also be formed. So you are melting batch wise, right? It's not entire, this material does not get melted at all. So that's why we call them partial melting. So you have a partial melt formed there, while there is rest of the materials are remaining solid. At a certain place, at a certain temperature, of course, everything can be melted, but usually that temperature does not reach the subduction times, because I mentioned that when the subduction takes place, at a certain point, what happens to the subducting plate? It will get weakened and weakened and break into two sections, right? So once you break this subducting slab, it will no longer subduct beneath, right? That means you are stopping the subduction, while one part will go deeper and deeper, and the other part want to uplift. So this uplifting part, which is available for us at a certain time later on, will be subjected only to the partial melting. But this subducting, the broken slab which is sinking down to the mantle, will continue that melting part, and maybe completely melted during the mantle. During it reaches the deeper part of the mantle, it will be completely melted. But the remaining part, being it is the subduction stopped, it will come back, or it will return. That means return means you are decreasing the temperature, okay, because you are coming towards the shallow levels. You are decreasing the temperature from high temperature. So no longer continuation of the heating will be there. Therefore, there is no opportunity for this particular rock to reach full melting. So therefore, we call this subducting slab is under partial melting. So at different temperatures, at different melting points, this gets melted. For example, the best example to understand is maybe in some rocks, if you happen to see close inspection of some rocks, you will do this at the practicals in our laboratories. You will see, for example, okay, I will draw somewhere here. If you take a portion of a rock, right, like this, you will see if this rock contained feldspars and quartz. Okay, if you had feldspars and quartz, you may see some of the quartz are like ribbons, very long, like this, right? Usually quartz is like something like this. You have seen that in rocks, right? That's a normal appearance. Feldspar is also same, right? Like this. It's not a ribbon like, right? But in some rocks, you see them like ribbons, very long, some few centimeters long, a single grain, single grain. How can this happen? This type of roundish grains to become ribbon-like features, what you need is you need to extend them, right? Some extension forces or tensional forces should be applied, right? This can happen while the temperature increases. Temperature increasing conditions, their plasticity conditions are changing, so that at a certain point they get melted, right? Before melting, they are getting extended with the tectonic forces when the pressure is also there, right? This is happening with the pressure also, right? When the pressurization is there, this extension is very easy. So when the temperatures are increasing and pressures are increasing, these roundish quartz becomes ribbons like this, and the next step is they get melted, right? They get melted, and some melt is generated out of that. But even when the quartz reached this stage, maybe temperatures like 700 degrees, feldspar does not behave like this. Feldspar still remains like roundish even at this stage. So that means the melting temperature or the deformation conditions, deformation plasticity limits of feldspar is much higher than quartz. So that means to melt quartz, to melt feldspar, it needs more temperature conditions, right? So maybe at a region like more 100 or to 150 degrees Celsius more, if you heat the rock, then feldspar may be starting melting. So but until that time, feldspar remains as solid, right? So this is a very good example to show about the partial melting, right? So the partial melting means the one portion of the rock started melting while the rest remains solid. Okay, so that is the idea behind that. And all these things depend on the original material composition. As you said, the original material composition is this one, right? This is the original composition. You had feldspar, you had quartz. If you had more things like olivine or some other pyroxene or some other minerals, then uh, depending on that, the stages of partial melting formation will be different, right? So it all about the bulk chemistry. We call it as the bulk chemistry. So when you have the different bulk chemistries, you will have different melting temperatures. Okay, and also not only that, the model percentages are also a matter. Model means how much quartz is there, how much feldspar is there, how much olivine is there, like that, right? The percentage wise, 10% quartz, 20% feldspar, like that, right? Because the amounts of the material which contributes to the melt is also depending on the amounts which are available at the original source. Okay, so that's what the idea behind the partial melting. So it does not uh, the melting does not happen together at once. That is the very simplest idea. Okay, is it clear?
Very clear, sir.
Okay. Right. So the partial melting and dehydration, decarbonation, everything happens. We call this region as the mantle wedge, right? So we call this mantle wedge because here you see the mantle. It's like a wedge, right? Wedge. You understand wedge? Yeah. The wedge is something like this. Sorry, it should be linear. It's a triangular like area, right? Wedge. So that's why we call it a wedge, the mantle wedge, this region. So mantle wedge is a mixed region. You have a lot of materials, sediments, melted materials, water, other magmas, everything is there. So therefore mantle wedge is a very complex area in the Earth's interior, because you have different compositional varieties there. So these and also these melts, I want just to connect one more thing for the partial melting. And you see these melts are formed at different stages at different places, and all these things are coming upwards because they are low dense compared to the remaining materials, because this material is heavy and dense, but melting is taking place only out of one material, so therefore it is low dense compared to the overall composition. So therefore it's low dense, and these low dense materials are coming up. So while they are coming up, they can mix each other, right? They can mix each other. Some are mixing together, we call miscible, right? If they can mix together, for example, two solutions, salt solution and a sugar solution, we can easily mix, but you can't mix petrol and water, right? They are non-mixing. So such non-mixing materials are called immiscible, and mixing materials are called miscible. So we have miscible magma as well as immiscible magma. So sometimes you may have or you will encounter when you read about the magmatic processes about miscibility, right? Miscibility and immiscibility. So that means the amounts of mixing of materials, different compositions, different magmas. So that can cause some variations as well, because some magmas can mix and come to the surface, whereas some are unmixing, and it separates out. So it separates out and come as a separate liquid. So for example, gold precipitation is happening because with sulfide magma, sulfide rich magma and silicate rich magma, they are unmixing together, right? They are immiscible. So we call liquid immiscibility. So this immiscibility causes one material to be separated out from the other one. Okay, so this gold like thing prefers sulfide rich compositions. Therefore if gold is available as a liquid, in the form of a liquid, it's available in magma. So this gold can squeeze out and penetrate into the sulfide rich magma when they are trying to mix together, right? They are unmixing, but gold can come as diffusion, uh, and it can be diffused into the sulfide magma. So sulfide magma, when it crystallizes at a separate place and silicate magma goes out, they can separate. That means the gold which was available in silicate magma can be filtered out by sulfide magma, right? So that is what you call the liquid immiscibility. So this is also a natural process where you have a kind of a mechanism for forming gold-like materials, gold-like deposits, metals, right? Actually, not only golds, the other precious metals, right? Like precious minerals, we have precious metals. Gold is one of those precious metals because they are very expensive. And what are the other ones? Platinum, rhodium, palladium, like things, we call them platinum group elements. So in the periodic table, if you investigate the periodic table of elements, you will see a separate group called platinum group elements, or PGEs, right? So these PGEs are unmixing with silicates, silicate magma, PG bearing material. So they like to go to the sulfide rich regions of magmas, and this magma, if separated out from the silicate portion, they can deposit separately. So the separating sulfide magma will be deposited here and crystallize. So you can mine this region and get gold or platinum or those things, crystallization. So anyway, all these things are related with partial melting. So this happens in the earth, mainly in this mantle wedge region. This is a complex region. Okay, so and this continental crust gradually gets grown by this magma, because magma is coming continuously during this subduction process, and this magma comes up continuously dumping materials over the continental plate. That means the thickness of this continental plate will get increased more and more. So we call continental growth is taking place, is happening at the subduction zone margin, right? This is the continental margin we call, because that's the edge of the continent where the continental growth is happening. But what is happening here in the oceanic margin? The oceanic crust is being destructed, right? It's being destructed means it's going deep into the mantle and it is getting melted and it loses some part, right? But that losing part is compensated by continental crust growth. So that means in overall mass consideration, there will be no more mass destruction. So this is a natural cyclic process where we have the mass balance in the crust and mantle. Okay, right. So this oceanic lithosphere subducts underneath the continental lithosphere, and oceanic lithosphere heats and dehydrates and further subsides, and the melt rises forming volcanism. So the melt rises from volcanism. So you can see the volcanoes formed like this in continental part of the plate, and at the margin, exact margin here, you are generating some ridges of mountains, right? So you can see here the Andes mountains. So these are the Andean mountains formed as a result of this complex process, right? This volcanism later on, after finishing, causes a crystallized mountain ridge. So this Andes mountains is a very good example for this type of continent oceanic collision. So previously we considered ocean plate collision, where Mariana Trench or the Japanese islands are the examples for such occurrences. Okay, right. So this is about continent oceanic crust collision, which we generally term as subduction, because oceanic plate is subducting towards the mantle. So that is the main driving thing, uh, the process which is happening for the subduction process for this type of tectonic situation. Okay. So now so far we have considered two tectonic settings where we considered about the convergence of ocean collision and continent ocean crust collision. The other one is continental collision. So this is the remaining one, continent collision. We have to consider now. Right. The typical example is Himalayas. The typical example is Himalayas. Okay. So you can see here, Indian plate is here, right? This is the Indian plate, right? In this map, you see the Indian plate, and the other plate is the Eurasian plate, the biggest continental plate, Eurasian plate. Okay. So you have two plates there. And you have the collision happening because this Indian plate is moving in this direction. Indian plate is moving this direction, and Eurasian plate is moving on the opposite direction, right? So both are continental plates, and there is no way to accommodate the space, because you see this is continental crust and this is also continental crust. Actually, there is no place to subduct. For example, here you had the mantle in this part, easily to subduct, right? Like here, but in this case, everywhere is solid lithosphere. Although mantle is there, but this does not go deep into the mantle because both are very robust, because there is no such buoyancy to carry this slab into the much deeper regions. So therefore, what is happening is when these two is colliding, one part is colliding this way, the other part is coming this way, both hit together. But there is, to accommodate the space, only thing possible is to bend them towards this direction, right? So bend them towards this direction so that you can have a mountain like feature. So that's why you have this type of a mountain like feature formed, mountain range formed. Therefore, you have this continent collision. For example, Alps mountains, European Alps, and the Himalayas. So in this case, you have these two stages of this Indian plate. Some time ago, you can see the collision just before the collision, the complete collision, just before the complete collision. The tip of the Indian plate is here and tip of the Eurasian plate here. because you know these plates contain a lot of original materials, very old materials, right? Existing materials are there, but collision takes place at very recent times, not very old times. Okay, but the materials composing them are very old. For example, even 2.5 billion years old, 2.5 gigaannums old rocks are there. Even in Sri Lanka, that is the case. I just explained for a question of some of you. Our mountains were formed around 550 million years ago, but actually the materials composing our mountains are much older than that, right? So likewise, these materials are older, but the collision takes place at a uh, younger time. Okay, so they collide together. Collision is taking place. So once this collision happens, actually there is no space, so therefore it's kind of a shearing is taking place, right? It's kind of a shearing, and which makes everything to make bending like these mountains, right? Because of shearing. So this shearing is taking place in different directions. Okay, so they bends the materials, and like here, so you have this material raised. So that is why we call the rising Himalayas. The rising Himalayas means they increase the height of the mountain. Even now, even just this moment now, some millimeters are changing the height of the Himalayas. Okay, some fractions of millimeters even change the Himalayas, but now actually it has come to the maximum compression, right? There should be some limit, right? There should be some limit for this compression, because if this continues, there should be like rising Himalayas like this. But you know, at a certain time, this rising is also, I mean, this compression, because you have compression like this, two forces, and this compression has come to a maximum level which can be tolerated by the two plates. So once this toleration exceeds, it tends to break, right? It tends to break into pieces, like faulting, right? So remember, we mentioned about faulting here, the fault. Okay, faulting means a brittle feature, so it's like breaking. So here we see some brittle feature, faulting, because at a certain time this will exceed its compressibility or extensional limits, plastic limits. So then it will break. So once this limit passes, they breaks, and uh, there will be sudden motion. There will be sudden motion. So that's why you have some, recently we observed some in the Nepals also, we observed some huge earthquakes. That is because of rupturing due to this compression, right? Great Himalayan earthquakes, right? Now, even now, the seismicity levels around the Himalayas are getting more and more increased because of this. They have reached to the boundary levels. No more compression is possible. So in this, yes, in the recent, or in the time to come, very I mean very soon, there will be a lot of earthquakes in this region. Like, I mean, there will be no much effect to the Sri Lanka, but in this region, I mean, this part will be a lot of earthquakes. Even now, we experience some earthquakes. So for example, in the Nepal, the country Nepal, there was a huge earthquakes some years ago, right? All are because of this type of compressions, right? But these places are about some thousands kilometers away from us, so therefore we don't get much effect on that yet, but in the future maybe. But that is some million years later, not in some 100 years. Okay, so anyway, the Himalayas, the boundary, this region, this colliding region gets risen, and it will lift this entire portion. That's why we have the plateau. That is why we call Tibetan Plateau. Remember, the region where the Tibet is composed, somewhere here, gets risen and made like a plateau like this. right? So Himalaya mountains are there rising, and this region becomes a flat region. Okay, Tibet and southern China region. So that is what you call the Tibet Plateau. So normally once you have a risen mountain range, always there will be a high plateau region on besides it. Okay, so this is the morphology, geomorphology produced as a result of continent collision. So in the central highlands also, right, we have high mountains, risen mountains, but you know Horton plains like places, that is the lifted part, and one side you have the world's end, the other part is the flattened area, right, Horton plains. So that is somewhere like this region. Okay, it's a typical mountain form, or what you call the geomorphology. Okay, typical geomorphology uh, you can observe due to continent collision. Okay, so this is all about the three types of convergent boundaries. The convergence, where we discussed ocean collision, continent ocean collision, and continent collision. So the typical examples for ocean is Japanese islands, for example, and Solomon Islands. And the second situation, continent oceanic collision, is Andean mountains, so, and the third place is a continent collision, where you see the Himalayas, the Mount Himalayas. Even you can relate the Central Highlands as well, right? Central Highlands is also same. Some time ago, this collision happened as a part of the Gondwana about 550 million years ago. But the Himalayas is now happening, right? It's the present situation. So actually, the Sri Lankan highlands were analogous to the Himalayas at 550 million years ago, right? We were like in the Himalayas at that time. Okay, any questions? Any questions regarding to this these three tectonic regimes? No questions? Okay, so remember, while these collisions take place, right? For example, here, so we are broadening the Indian Ocean as well, right? We are broadening the Indian Ocean as well, because you see, there is motion like this, and in the place where we have the Sri Lanka is lying somewhere here, right, and southwest of Sri Lanka, still the Indian Ocean continues, and in this some 2000 3000 kilometers away from Sri Lanka, there is a mid-ocean ridge is there. We call it Southwest Indian Ridge, right? Mid-ocean ridge, remember? Mid-ocean ridge, it's somewhere here. This is the mid-ocean ridge, this part, mid-ocean ridge, where we have the Southwest Indian ridge, and Indian Ocean is also moving from this towards this direction, from this part, and towards this direction, the other part. So that means this Indian Ocean is also moving. It is facilitated by this collision as well, because the same direction, and but the regions where we have this part in the southeast region, the Indian Ocean is moving this way. Okay, Indian Ocean plate is moving, I mean Indian Ocean part is moving this way. So the broadening of Indian Ocean is taking place in this side, in this direction, whereas the compression of the Indian Ocean is taking place from the southwest side, right? So it's a complex type of activities taking place, and you can understand there should be different physical conditions prevailing in these regions. Physical conditions means always pressure and temperature changes. Okay, is taking place due to this complex type of motion. For all of these motions, what is the initial driving force? It's the mental convection. So the mental convection is the driving force. The mental convection is the driving force which is taking place in the ocean. Okay, sorry, in the mantle, in the upper mantle, which is taking place in the upper mantle. So due to that, all these complexities have been created within the earth, right? So this is all about convergence and type of divergence, sorry, convergence, and some examples of the historical movements of the Indian plate. So we were like moving together. This is about 71 million years ago. Okay, this is about 71 million years ago, the position, and then 55 million years ago it moved, because this is moving towards a direction like this, colliding with the Eurasian plate. Okay, and about 38 million years ago here, and 10 million years ago like here, and currently it's now here, right? That's why I mentioned that it has reached to the maximum compression level. It has reached to the maximum compression level. Has reached to the maximum compression level. So you can see the Mount Everest ridges, the different ridges of Mount Everest composing various types of rocks, because the melting and dehydration and everything is taking place here as well. So you have this type of situations. And you know, I mentioned that this type of this region of continent crust is very thick, the thickest in the planet Earth, Himalayas. This thickness, this continental plate thickness is how much? It's like 70 kilometer, right? It's 70 kilometer means it's 10 times, more than 2 times greater than the thickness of our continental region, the place where we are lying, right? It's thick, so 70 kilometers means it's exerting a huge pressure towards this region, right? In the deep part, 70 kilometer thick rock layers means huge pressure, right? It's like how much? 10 kilobars is like 30 kilometers. So 70 kilometers means 20, more than 20 kilobars. So more than 20 kilobars is well enough to convert graphite into diamond, right? It's like eclogites. It's same as eclogites. So in eclogites, we have diamonds. I mentioned we have diamond in eclogites, right? Remember, in the Central Asian region, like Kyrgyzstan, Uzbekistan, Russian, Russian, like those region, Kazakhstan. Okay, that regions there, some diamonds is there. So similarly, in the Himalayan region also there are some diamonds found, but at deeper levels. But when it comes to erosion, gradual erosion, right? It takes some long years, many years, some hundreds of million years to erode this part and expose this deep interior into the to expose the diamond, because diamond is there in this region. But there are situations where this towards the western side, like this part, right? In this part, if you consider this part means towards a region like here, right? So this region, because of high heat, even here magma is produced as usual, and this magma sometimes bring this deep diamond which is available here, with this magma, right? With this magma, diamond is taken up. So that's why, what is the country somewhere here? That is Pakistan. Okay, in Pakistan, some part of Pakistan, there are some reports of occurrence of diamond. Okay, that diamond is formed at this deep levels, and those diamonds are being taken up by this upcoming magma. But that magma is different from the magma that you bring a huge amount of diamonds in Africa, right? That African diamonds are brought by the deep interior of the mantle, right? Somewhere like very deep, like 200 kilometers below, right? Very deep interior. That is a deep interior of the diamond, which is brought by magmas. That is rare magma. I mean, it does not come to the surface every time. So it's they are, and also they are coming as pipes, right? So like this, like pipes, they are coming as huge magmas to flows, but rarely. But if it comes, they carry huge amount of diamonds with them, right? A lot of diamonds are coming, and these diamonds are even spread over the surface. You can pick them while walking, right? In river channels, they are spread, right? In Africa, you can search in the web. You will see some locations where people collecting diamonds, like in a gravel bed. We are finding gems in a stream, in dry streams. People try to collect, pick gems in Sri Lanka also, right? So similarly, in Africa, people try to collect diamonds, but actually it is not allowed because these all these diamond regions are taken up by the governments and some companies to mine. So therefore, average people cannot access those places, exposed regions. But uh, accidentally, people find such regions. Okay, so but that diamond is different because they are coming from the mantle directly. I mean, the composition is same, nothing structural changes are not there, but they are very pure, right? As I mentioned, there are no inclusions and all. Very pure diamonds are there. But the diamonds which are generated as a result of conversion of graphite into diamond may contain some impurities as well, right? So that has to be carefully inspected. Like you are examining gemstones with gemmological microscopes to for inclusions, right? If you have a lot of inclusions, then maybe they have low value, and opposite is also there, right? So if the inclusions are orderly arranged, like for example, needle like inclusions in some stones, you have rutile needles like, right? So then it adds extra beauty to the gem. So then the gem variety becomes more expensive than the normal one, being having these inclusions, right? So anyway, uh, in the region of Pakistan, you have this diamond because of this bring up of these deep diamonds, which is produced as a result of conversion of graphite, because graphite is there in the continents everywhere, right? We also have graphite, a lot of graphites, right? But our graphite does not reach this depth. It reaches somewhere here only, about 30 kilometers, right? So it does not change into diamond. But these diamonds are formed as a result of deep. It's not subduction actually; it's collision. But the two continental plates are meeting together, so that one is almost like on top of the other, right? So here 30 kilometer and here 30 kilometer. So the overall thickness is 70 kilometer, right? So we call the crustal doubling. Crustal doubling, that means two continental plates are pasted on top of each other, like, right? So this part is the crustal doubling is taking place in this part. Okay. Even though we show this as a very small sketch, this part is some thousands of kilometer wide. Okay, it's not a small region. It's some hundreds or thousands of kilometers wide in some regions. So therefore, this is possible, right? So this background knowledge is important for you as gemologists, because now actually you are in the market as gemmologists or as gem traders, but without knowing much of the scientific aspects of these processes and also the chemical processes which converts these chemical reactions and all, right? So but you have very good experience. I'm sure some of you have very good experience over many years in the gem trade, and you are very, even some people are there, maybe you also inclusive of such people, they can even give the refractive index of each and every gem variety once you see, even to the second decimal point, right? I have met such people, right? Even for us it's not possible, right? Because we are not in that field, but we are in the geological field. Also we are talking about the genesis and processes. We can explain and interpret those things, but we are not doing this. I mean, we are not dealing the variety all the time, right? So therefore, once we need the refractive index to the exact value, we refer the relevant textbook sometimes, right? For the normal varieties, we know, for example, quartz is like 1.1, 1.5, like the glass, right? Is the same as glass. It's simple, but I'm not referring to that. And for example, if I ask what is the refractive index of a sapphire, right? One might answer to the second decimal point, right? I mean, there is no need for keeping them in mind for people like us, because we are doing the scientific research. But for you, it's your full-time work, right? So you need to have it in your hand, always ready, right? Otherwise you will lose the business. So therefore, anyway, the purpose, one of the main objectives of this gemmology course is to supplement the gem people in Sri Lanka with the scientific knowledge and all required crystallization processes. For example, crystallography knowledge, right? It's very important, right? You are maybe interpreting gem crystals by experience. You can see, you can find all these what do you call it, vacu, and all other features. There are several things, right? And crystal phases also you can see by experience. But if you ask to explain them in terms of how they formed and what are the possibilities of changing them, for example, if the mineral is a twin varieties, you will learn about these twin minerals. Some bunches of crystals, they grow together like a plant, right? uh, you will learn about theories. So to supplement that knowledge is the main idea behind this one, because you need not just to sell a mineral. I mean, a person who is a gemologist, who has a scientific knowledge as well, not the trading experience, must be able to develop this material to a higher value, to attain to add more value to the gem. For example, zircon is still considered in considered as a semi precious stone. Why can't we make it a precious stone, right? You have to modify the qualities of the stone. For example, even gewder, we are changing, right? We are changing the properties of gewder to make it corundum. So that means we are adding the value to the stone. But why can't we do that to the Amazonite, right? The feldspar variety. It's a feldspar, but it's a beautiful variety, right? So we can improve the quality. So for that, you need the knowledge, scientific knowledge, some experiments. The foundation for such processes to enhance in the value addition to the minerals, for the gems actually mainly, is very important. So that you need the basic principles. That's why the PGIS has started this course some times ago, right? Even some people you may know who are in gem field have now MSCs, and they conducted much more research even during MSc and after that, and they have invented with some products. For example, some furnaces, some new furnaces. We have traditionally we have the Lakmini furnace, but now there are several other options for that as well, right? Some developed ones. The some more higher temperature conditions can be reached, or such experiments should be taken place. I mean, without affecting the stone, how can you do? What are the fluxes to be used when you heat a stone? Because you have to add some fluxes, otherwise the gem might be melted out, right? to to reduce the melting point, like the same principles as partial melting, right, we just talked about. If you can artificially control the melting point, then you can expect that mineral before melting to reach some better qualities, even the color enhancement at least, right? Or some other physical features to come up. Even for zircons, for example, right? Zircons, there are several research going on to color enhancement and property enhancement, right? So, and several other stones are also being tested by different people in even Peradeniya University, under who have, I mean, who have got the foundation with the MScs. Okay, so that is the idea behind that. So I think it's very important that you gain the knowledge to improve the products, right? For example, even apatite, you think about the apatite deposit we have in Epavala, right? Apatite is a very low value mineral, but still it can be considered as a gem quality mineral, for gem quality mineral with low value. But if you enhance its quality, it can exceed the value of certainly zircon, more than that, right? There are huge crystals, single crystals of apatite. Have you been there to the Epavala deposit? Even human sized crystals are there, apatite crystals, single crystals. You go and see there, right? So, but nothing is taking out of that. And even you remember the place where we have Pulmude ilmenite rutile, right? We are exporting bulks as it is, right, at very low cost, some few tens of dollars per kilogram. But how it comes back to Sri Lanka, some thousands of dollars worth titanium or some other value added products, they are coming back to us. They are selling back to us. They buy from us for $7, and they are selling the product at $1,000 to us back, right? Graphite is also same. Graphene, now graphene is produced out of Sri Lankan graphite. But what is the price of the 1 kilogram of graphite being exported from Bogala, right? This Germany is exploiting. The Germany is exploiting the resources, right? So mineral policies should be made. Actually, mineral policy was made. I was also one part of that committee on the science and research ministry, but still it could not be implemented. The government, when the governments change, they change again. One ministry passes the ball to the other, and officials are changed. So the new people have to be learned it from the scratch again. So you start, some years lapse. It's just a waste, right? So we are fed up with this system sometimes. Okay, so as the people who are directly involved in the field, so you should think of this type of avenues which are in front of us, but maybe we are not utilizing. Okay, right. So any questions up to this? Any questions up to this point? No questions? So today I want to stop for the time being. So if you have any questions, you can ask now. No questions? Everyone got clear? Okay. So then, okay, I forgot to mention that I think you have typed your name, right? Name and your number. If not, please put it into the chat box because we need the attendance. Okay, so then shall we stop here for today? So I will upload the video at last. I will send you the materials plus the PPTs as well. Okay, so let me conclude then for today. Before that, please type your name and number if you did not do that yet. Okay, so let me stop then. I hope everyone typed your names. Right, so let me stop then. So see you next time.
Thank you, sir.
Thank you, sir.
You're welcome.
Thank you, sir.